let us finish the previous lecture. What we're left to do is to calculate the staggered part of the charge density, the sign alternating part of the charge density, which is caused by the fact that the translational symmetry was explicitly broken by construction. The sequence of alternating atoms AB, AB actually implied that the levels, the localized levels at corresponding atoms were shifted one with respect to the other. As a consequence of that, the distribution of charge is not uniform as it was before in the translational symmetric case. So there is an excessive charge which alternates in sign on top of the average charge density, which is still there, of course. And we would like just to know how this excessive charge, this staggered charge, looks like. And we have shown that in the limit of, I will call it ionicity, or ionicity, if you wish. In the limit when delta is much greater than the hopping amplitude, we have the nice picture of the charge distribution when pairs of electrons with opposite spins would sit on the lowest levels, say belonging to sublattice B, whereas the levels belonging to sublattice A were completely empty. That was an extreme case of this charge distribution, redistribution, which resulted in a very strong charge density wave, the alternating sequence of positive and negatively charged centers, with a huge magnetic field inside, a typical ferroelectric, and things like this. That was a kind of, and I ask you just to look at the elementary excitations in that limiting case, how they look like, how would you build up an excitation, how that excitation would delocalize, and how would you make sure that these excitations are gapped. So there is a finite energy required to create such an excitation. But we are now interested in the opposite case when delta is small compared to hopping amplitude, or better to say compared to the bandwidth. The band is wide, and the gap is generated gap is small. And in this particular case, calculations must be different based on the realization of the Hamiltonian, which of course includes the hopping, the translation variant part, and the ionicity, the term generated by the delta coupling. So let me again remind you of the model. The model was quite familiar. In the beginning you have just the standard type bonding part. And on top of that, you have the sign alternating part of the ionicity. What we did, we passed to the momentum representation. Then we said that if we have the CK, which is the Fourier transform of this C and sigma operator, I don't write sigma. The spin plates and all this business are very passive role, so this is why I'm not paying much attention to it here, at least. So CK would be denoted as A of Q if K belongs to Q, which means that K, I remind you, it was the quasi-momentum originally belonging to the standard Brillouin zone. And there is another momentum Q, which is inside, is where is inside in this Brillouin zone. But the new Brillouin zone is the reduced Brillouin zone corresponding to the period doubling, and we anticipate that this should be the right description just because the alternating sequence of atoms A and B makes the unit cell not elementary, it becomes diatomic. So again, I show what is k? K varies from minus pi over a naught to pi over a naught. Somewhere here we have 0. And the 1/2 of that is just the interval when we define the wave vector q. And then either k is equal to q, in case when k is somewhere inside this Hilbert zone, or if k is outside, I can always represent it as q plus q large, when q large is just this distance, 1/2 of the reciprocal eddy spectrum, or the perfect nesting property vector, because this is an important part of the story, because of the spectrum epsilon of k, which is twice t cosine k a naught, a very important property, is satisfied. K plus q is minus epsilon k, and this is known as the nesting property. Nesting. It is just this very property which makes the metallic state eventually unstable, which causes lots of instabilities of a metallic state in 1D because just of this property. So if k is q, then it's aq, but in case k represents q plus q large, then we have bq, and so we have a new basis of states, aq and bq. And the Hamiltonian, in this case, takes the suggestive form, if it's less than pi divided by a naught. Epsilon of q, I have already defined it here. AQ dagger AQ minus BQ dagger BQ. This minus BQ dagger BQ, this minus sign just is a consequence of this property. Just of this property. And plus delta A dagger B plus Hermitian conjugate. That's how the Hamiltonian looks like. What we did next, we said, okay, all right, in your lecture notes you have the standard diagonalization of this Hamiltonian using the UV transformation, Bogor-Lubov transformation, but not the one for the bosons, but the one for the fermions, since the transformation for the fermions is nothing but the rotation in the effective spin or isospin space. This is why we involve this analogy, and we introduce the spin law, which is AQ-BQ. Right? This spin-off may be subject to any special unitary transformations. And then we can rewrite this Hamiltonian as, okay, let me put it like sum over QHQ. And this partial Hamiltonian HQ as psi of Q dagger, the 2 by 2 matrix H of Q psi of Q. When this matrix, as follows from this structure, has a form epsilon q times tau 3 and plus delta times tau 1, and has the form epsilon q minus epsilon q delta delta and delta. So if you plug this matrix into here and do all the contractions, of course you will arrive at this expression, but it's high time to appreciate if you have objects like this, A dagger A minus B dagger B, and A and B are components of the spin-off. It's of course a tau Z, Z components of the Pauli matrix interleaves. Whereas here we have the symmetric mixture of the two A and B with the plus side, then it is tau 1. If it were with the minus side, it would be I, imaginary I, times the tau 2. So all the possibilities are exhausted there. What remains not to be accounted for would be just a chemical potential term, which would be A dagger A plus B dagger B, the trace of psi dagger psi, but we don't write it because we know the number of particles is precisely equals to the number of lattice sites. There is exactly one particle per site, and the chemical potential corresponds to the exact particle hole symmetry. Its mu is equal to 0. So this is why such terms don't appear. So the diagramization of this form is very simple. What we did, we said the following thing. I will just skip, I will suppress Q because Q appears here as a parameter, nothing else. I will simply introduce a SU2 transformation. This new chi is, well, just in this instance, let us keep this alpha Q. And this is Q, and here I have spin built up of two components, not A and B, but alpha and B. It's a new basis. So this is the original one, A and B, and this is a new one, alpha and beta, and this is a rotation matrix, the SU2 matrix, which I choose to be I some theta divided by 2 times which matrix, Pauli matrix is tau 2, and which can be written as the cosine of theta divided by 2 plus I tau 2 and the sine divided theta naught. Such a unitary transformation, of course. W dagger W is 1. It's a typical SU2 matrix. Why do I rotate around about the tau 2 axis? Because I have here an interplay of tau 1 and tau 3. What I want to do, I want to further mix them up. So they are already mixed. They are already present here, both of them. One with the kinetic energy, the other with the potential. Now with this rotation, what I'm going to do, I will find out now the transformation laws for these Pauli matrices, and when I use them and express the transformation, this rotation in terms of theta, I will plug all into there and require that the term containing tau 1 must vanish. That's the very idea. When you have something bad, you add a kind of medicine which is also bad. And this one bad kills another, you are the other one. That's how the doctors do, actually, right? All right, so what you can do, first of all, the combination psi dagger H, psi goes to chi dagger H tilde chi, when H tilde is, of course, W minus 1 H W. I think this must be clear because what I did, I simply plug this expression into this. And then psi dagger, of course, will be chi dagger times W minus 1. So I get W minus 1 from the left, W from the right, altogether I have. It's a typical quantum mechanical operator transformation of the Hamiltonian. And the Hamiltonian, these are the SU2 matrix defined here. And here, your Hamiltonian H contains Pauli matrices. So you would like to know how these Pauli matrices are transformed. And it turns out they transformed exactly as you would expect them to transform. It's cosine theta tau 3 plus sine of theta 1 and W minus 1 tau 1. W is minus sine of theta tau 3 and plus cosine of theta tau 1. It's nothing but a planar rotation, so you imagine a three-dimensional pseudo-spin or tau, if you wish, matrices space. And what happens here is just that you had some vector in the basal plane. Your Hamiltonian was this vector, because as you can see, this is the same as some magnetic field B times tau. But the magnetic field has two components, along 1 and along 3. It's not, I'm sorry, I made a mistake. This should be not this plane, this should be this plane. this should be something like this. And what you do, you would like to make a rotation of your spin coordinate, spin axis in such a way, in the plane tau 1, tau 3, that the new magnetic field is now directed along the new thing from z direction. And that gives you an idea what happens in with the tau 3 and tau 1 matrices. This is the transformation laws. What you do next, you simply build up this H tilde. Right? I will not do it for you because you can do it for yourself. Instead of this H tilde, we'll be just looking at what we have here. Tau 3, right? So I would have to push all this thing here. And plus delta, and then I would have to push all this thing here. And I will collect terms with tau 3 and with tau 1. And I would say the coefficient in front of tau 1 must vanish. And that will define the appropriate value of theta. And this appropriate value of theta is given by defined by the relation tangent of theta of q is minus delta divided by epsilon of q. I would like to point out that this quantity is positive because the energy cosine q a naught, or the q, which is measured by divided by 2a naught in this region, this quantity is negative. Is negative, yes indeed, because the cosine is positive. Cosine is positive, the minus sign in front is negative, this is negative, minus sign here. Altogether it's positive. And then you write down precisely what you want. You will write down the sine of theta of q, which is sine over cosine, right? Delta divided by e of q, and the cosine theta of q must be minus epsilon of q divided by e of q, where e of q, you already know this, is nothing but epsilon q squared plus delta squared, which is the same as 4 times p naught squared cosine squared q a naught plus delta squared. So, this is already the solution. The solution, because we know we have found all the quantities. If we carefully look at the consequence of this relation, we will be left with the conclusion that h tilde of q is nothing but the minus e of q times tau 3. This is what you will find out in the end of the day. So therefore, your Hamiltonian h of q will have the following form. It will be epsilon of q. First you will write down beta q dagger beta q, and minus alpha q dagger alpha q. Why first beta? Because of this minus sign. So your Hamiltonian, here your Hamiltonian is the same as chi of q dagger e of q minus tau 3 chi of q. If I write down this is in components, I will find out precisely what is written here. So this is fine, because this already gives me not only the spectrum, which we had already derived the spectrum anyway, it was not a problem for us. derivation of the spectrum, a particular problem is much easier than the realization of the whole and alternatively with the functions. The second problem is harder. So all information about the spectrum is this, but all information about the wave functions is this. It's all about the yeah, so since this is a positive definite quantity, and since the number of states in the whole Brillouin zone was n, so the number of states in the reduced Brillouin zone is n divided by 2. Then you have n divided by 2 q states in the reduced Brillouin zone. But if you take into account the spin degrees of freedom, we have to multiply it by 2. So it turns out that the total number of physical states, one particle states, each state being parameterized by q and the spin projection. Two quantum numbers, q and sigma. So therefore, it is only the lowest branch which should be filled for the ground state to be built. Your spectrum looks, as we already anticipated before, it looks like this. It's a nice looking spectrum with a finite gap. What is written here is just E of Q. This is energy plus minus. This is Q, which varies in the reduced Brillouin zone. These are form Fermi points which are split. The gap is this one. This is delta. So this distance is twice delta. This is the conduction band, and this is the valence band. And the valence band, in other words, the lower band contains n states altogether, and all electrons go just there, because this gives you a minimum of the total energy. So you have a state in which the lower branch of the spectrum is completely filled, the upper branch of the spectrum is completely empty. And the two branches are separated, the two bands are separated by a gap. Of course, this is an insulator, by definition. By the band theory, it's an insulator. So, mathematically, this means that if you build up a ground state, this ground state should operate as a standard mathematical vacuum for beta particles. Because the upper branch is empty. On the other hand, for the alpha particles, we have precisely this result ensured by the fact that each Q state in the lower band should be occupied. But that gives you a prescription how to calculate any quantities in the ground state. Of course, at a finite temperature, you will have excitations from the lower branch to the upper branch. But of course, any thermodynamics will contain this extra factor at lower temperatures, which will in many ways devaluate all your efforts to obtain anything nice. Everything will look very trivial. All thermodynamics will be exponentially suppressed if the temperature is much smaller than the band. So we are left with the final thing to do. That was just kind of a reminder of what we've done. So we would like to now to calculate the staggered average staggered density in the system. This is pretty straightforward. So you write down rho of n, which is the average value of the sum over the spins, C and sigma dagger, C and sigma. This is the definition of the local charge density or particle density at the given site, and I sum over the spins. This is quite natural. What I do next, I simply go, I say I can see that it's in terms of n, I have a trace, therefore, of course, yes, let it be as it is. Let me write down this as 1 over n, sum over k prime, sum over sigma, ck sigma dagger ck prime, sigma, average, and exponent k prime minus k, and a. Now, please check if you agree with what I wrote here. What I did actually, I expanded the standard C operators, fermionic operators in real space representation, in other words, in linear representation. I went from linear to the block representation in terms of k and k prime. Right? Now, at this very point, what I should take into account, the fact that in the original formulation, it's all the way, it's important to keep in mind, or to remember all the steps of your derivations. Because at different points, different representations may be useful. Here, for instance, I should not think in terms of Q particles, so they will come later. The particles in the reduced brilliant zone, I expand my Hamiltonian. Remember how my Hamiltonian was expanded in the standard basis within the undeformed, undistorted brilliant zone. And that looked as follows. There was a diagonal term and there was an diagonal term, which looks like this. There was a term when k was coupled, k prime was the same as k, and here k prime is k plus q large. Why? Because the periodic potential has a Fourier component at non-zero q, it's sign alternate, therefore q large is there. Right? Now from this I conclude that if I have this average may be non-zero in two cases. When k prime is equal to k, ck sigma dagger ck sigma. And here I have nothing because k prime is equal to k. Or in case when k prime is k plus q, because there is such a contribution on the Hamiltonian. So therefore, the second term is 1 over n, sum over kq, the average ck dagger ck plus q. And here I have I, q, n. Well, here you go. So, it is absolutely obvious that from very general consideration that this quantity must have a non-alternating piece which describes the average value of the charge density. And this average value of the charge density must be equal to 1, because on average you have 1 electron per site. Right? All the rest is something on top of this, but this must be guaranteed for sure. So this is, let me denote it by rho average, and this is exactly the definition of this one. But here I can find an Axial contribution, because what is written here is minus 1 to the power of n. By the way, what is written here is minus 1 to the power of n. Just precisely the alternating piece. And this I will multiply by the staggered component, where the staggered component, rho as staggered, is defined as 1 over n, sum over k sigma, and the average ck sigma dagger, ck plus q sigma. So this actually, the very definition of the density and the fact that the Hamiltonian has two contributions, diagonal and off-diagonal, immediately lead you to the conclusion that your average value of the density, that the average value of the density at the given site, and number 1, does contain the average contribution, which is this one. It remains to be shown by you as an exercise that this part is exactly one, doesn't contain any corrections. It must be just one. Has to be. And this is an extra contribution, the most important one, which contains a sign alternating factor, which means that if you had, on average, if you measure rho as a function of n, and here you have these n's, then you would have a constant part, which is a rho average, and on top of that you would have some kind of oscillations. And this is the height of these oscillations, this quantity, which is rho st, we would like to, where after that we want to calculate. Now from here we immediately conclude a simple thing that if I'm looking at this expression, I would like to continue this expression, and this continuation should look like as follows. 1 over n, I can now go to q, and sigma, I can now, without any hesitation, sum over sigmas, because the rest does not depend on the sigma. It's twice divided by n. Sum over q, which is less than pi divided by 2a naught. And here I have, if k is q, then it is a of q. Here I have bq, and of course, by symmetry, if k is k plus q, then it is b of q. And then this, the double shift by q, since 2q is the reciprocal lattice vector, is the same as a of q. This is how it looks like, and this is nothing but twice over n, sum over q, less than pi divided to a naught. The average value of psi of q, tau 1, psi of q, full stop. Now, if you do everything carefully and accurately, you will plug this, you will rotate your tau 1 in the way it is shown here, just in the way it is shown here. And then I will skip the details of this derivation. I will simply continue here. And you will sit down quietly, peacefully in the library or at home, I don't know what you prefer. And make sure that indeed the result looks as follows. The staggered part of the density is given by minus twice divided by n sum over q sine of theta of q. And here is the average value alpha q down in alpha q. Minus beta q minus beta q. Right. This is 0, of course, and this is 1. So we are left with minus twice divided by n. That's fine. It's good. Now you want to transform this sum. This will give you the length of the system divided by 2 pi. The integral from minus pi divided by 2a naught to pi divided by 2a naught dq. And the sine of q. And the sine of q is this one. It's delta divided by epsilon of q, which is 4 times t naught cosine square qa naught plus delta squared. Right? So L divided by n will give us just a naught. It's clear, right? And I will now introduce a new variable. I will call it p. which is dimensionless, QA naught. So I will remove this A naught, I will remove A naught here, I will replace QA naught by P. I will integrate over P. I will remove this and write down 0 and write 4 in front because it's an even function. And then all in all, I will get minus twice delta divided by pi, and this integral remaining. But let me also push 4 times t naught squared twice t naught outside, and I will get the integral pi over 2a naught, then p
Pi over 2.
What? Pi over 2, yes, what?
Not 2a0.
So what's the problem? Where is the problem? What did I do wrong? Ah. Dimensions, that's right. Cosine squared p plus delta squared, small. And delta is delta small divided by 12 dimensions quantity. So all in all, just let us remove all these nasty things. Delta divided by p t naught integral. So what is important for us now is the fact that we are in the weak coupling regime, assuming that delta, the amplitude of the staggered potential, is small compared to the bandwidth. So therefore, this is a small quantity. I like for certain to choose delta to be positive, but the sign of delta doesn't matter. As you can see, it's only interested in the square. So delta is a small parameter. So therefore, the integral is contributed mostly from the region of pi of momenta when cosine is small. Because if this is small, the integral will be large if the whole denominator is small. So I have to look into the region of pi when cosine is small as well. Right? And this is the vicinity of the upper limit. So nothing then prevents me to do just this transformation. Yes. Yes. And then this is the integral, which is just the same as it is there. Again, this interval gets mapped onto itself, with the only difference that the cosine is replaced by the sine. And again, as I said, this integral is basically contributed by the small values of s. Of course, those of you who would like to, love these coefficients 1, 2, pi squared divided by 85, I don't know. We'll go to the library, take a thick book, find this integral in the series of tables and integrals, and expressing it in terms of some elliptic function or whatever. I don't want it. Theoretical physicists must be able not to calculate integrals, but to estimate. If you have chosen your accuracy, then within the chosen accuracy, you must be responsible to keep all the terms within this accuracy and drop all the others, which are much smaller. Now let us anticipate the type of integral which emerges. When s is small, I can replace the sign by its argument. So I will get something like square root of s squared plus delta squared. If I didn't have delta, I would have a typical logarithmic integral ds divided by s, and it would be infrared divergent. It will be divergent on the lowest integration limit. It becomes convergent just because of this delta. The delta cuts off this divergency. But since the delta is small, the huge interval when this s being much less than 1, but much greater than delta, still remains. And within this interval, I can forget about delta and recall it only at the moment when I will hit the divergence. Then I will replace the lower limit by delta. In other words, I anticipate the result to be proportional to the logarithm 1 over delta. This is what I can immediately see without any calculations. Common sense tells me that. Now, the logarithm is a funny function. The logarithm is a very serious function when this argument is very small. Then the logarithm is negative and huge and varies very rapidly. But if the argument is positive, the logarithm is a very, very nice function. It's not really a function. It's a very slowly varying function. Much slower than any power of argument. Log of x goes in something like this. That's a function which increases very slowly. Much slower than much slower than exponential is nothing to describe. Much slower than any power. Right? And therefore, the people, especially mathematicians, mathematical physicists, I would say, and physicists, theoretical, invented what is called the logarithmic accuracy. This has been done, of course, in high energy physics because all these tricks and all these integrals had emerged already many, many, many years ago in high energy physics when people, for the first time, were found the necessity not to stick to a certain diagram, certain Feynman diagram, but instead start summing them up according to a certain principle. The logarithmic accuracy means the following things. If you have an argument a, which is much greater than 1, and you have a logarithm a, to you, the logarithm a or logarithm c times a, when c is of the order of 1, is the same quantity. Because what is written here is a logarithm a plus logarithms of c, but c is of the order of 1, maybe slightly greater than 1. The log of c is a number of the order of 1, and this is a huge number. Who cares about this small addition with respect to huge logarithm? This is precisely what is meant by logarithmic accuracy. You single out the most important contribution. You neglect the corrections which are. And with this accuracy, such a replacement, to me at least, as a person who has worked a lot just with these logarithms, means just the same. The lower limit is delta, absolutely, of course. The upper limit doesn't matter because s is much smaller than 1, s will be much smaller than pi divided by 2, and the replacement of pi divided by 2 by any constant like c here doesn't make any change. So this gives me just the minus delta divided by pi t naught as the logarithm 1 over delta, which I will write down as 2 t naught divided by delta modulus. Now, as a responsible person, I have to write down this plus a possible correction of the order of 1. This is a large quantity, doesn't exclude the correction of the order of 1. All my manipulations, if you go to the library again and find out the exact result, and then check what happens with that result in that limit, you will find out that what is written here just precisely the point. So, what I don't know, the coefficient here is robust. Every time you deal with logarithm, what stands in front of the logarithm has to be calculated absolutely exactly. It's crucial. When you have to deal with the logarithm itself, whether you write down 2 t naught, or 4 t naught, or 25 times t naught, this doesn't matter. So it sounds a little bit ridiculous, as if I'm not serious to say that things, but in fact, that's precisely what's going on. This is what is called the logarithmic accuracy and the asymptotic behavior of logarithms. So this is the final result we arrived at. You can see that the staggered component of the charge is of course proportional to delta. as it should. But it's not the whole story. It also has a multiplicative factor of the logarithm. It is very, very important thing. It turns out that it's consequence of something deeper than it looks like. You may find this calculation in my lecture notes, or you can do that by yourself, but you may ask yourself the following important question. Delta is a control parameter. I may switch it on, and then I will have an insulator. I can switch it off, and then we'll have a metal. I know how to calculate the energy of the half-filled metal. The energy is at delta equal to 0. But I also would like to know how the energy of an insulator looks like as a function of delta. How the energy of this very model looks like when delta is not 0. Here we have calculated only the charge density way, the stagnant component of the charge. It turns out that there is a very simple trick to squeeze out from this result the expression for this difference. Very, very often just what people are interested in is this quantity in units per lattice side, because it's an extensive quantity, and therefore the total zero state energy, the ground state energy, perhaps 0, 0. Let us recall the picture of the ground state. So remember, this is K times A naught pi by 2 minus pi by 2 minus pi. So if I had stayed in the original Brillouin zone, I would get this picture and continuation here. But I have mapped everything onto the reduced Brillouin zone. I have a lower band under the upper one. So the metallic state would be the state with a simple cosine band. And if I had mapped everything onto the reduced Brillouin zone, I would get the degeneracies at the two Fermi points, minus Kf and plus Kf. So the effect of delta is just to split this degeneracy, as it's going to shown here. But now you see that, as a result, the branch which is filled gets curved. It gets more negatives than it is here. There are some states approaching 0. There are no such states which are approaching 0 energy, are all exactly negative, from which you conclude that this quantity must be less than 0. And this is a signature of a potential instability of one-dimensional metallic state. And this is an example how it can become unstable. Here it becomes unstable, so to speak, by brutal force, by quantum chemistry. I use a compound in which I can move some atom in one position to another one, or replace one atom, substitute one atom by another one, and get from one component system to component system, A, B, A, B, A, B, and then get this picture that we have. But this also may happen spontaneously, for instance, by the coupling with the phonons. And this is the famous Paris transition, which all is about the same stuff as we have done here, with the only difference. Here, we broke the symmetry, translational symmetry explicitly. And in the Paris system, the symmetry is broken spontaneously in the way of a second order continuous phase transition. But this is exactly the signature of the fact that the metallic state cannot be very stable with a half-filled bed, because it can lower the system, can lower its energy by opening a gap. But opening a gap this example tells you, will be required, will be guaranteed, ensured by quantum chemical reasons. But if this happens self-consistently due to the interaction of the electrons with some other degrees of freedom, then you have to pay a certain price because on this reconstruction. So it will be always an interplay between two tendencies. One, electronically you would prefer to get your energy as low as possible. In other words, electronically, the electronic part of the energy is always advantageous to have it negative, as negative as possible. But on the other hand, to find the reason for that will cost you an energy with other degrees of freedom. So it's an interplay. So those of you who are interested in this question can look into, again, my notes and see the section electron phonon interaction and the Pilot's condition. There is an elementary introduction, and there are very interesting things happening there, because there you will find the new class of elementary excitations called solitons or kinks. These are topological excitations, not the standard ones that we are accustomed to. Maybe we'll organize a seminar, maybe if you have time and you have goodwill to do it. This is basically it. I can't add anything to what I said. Yeah, this is basically it. Well, the only thing is that there's this ground state energy. Did I write it down or did I not? I don't know. So this difference goes as minus delta squared divided by T naught, maybe pi, maybe 2, I don't remember, delta squared times the 1. T naught divided by delta. So that's the typical expression for the energy difference. And interestingly enough, this is an extremely universal formula, but maybe I have to say a few words about it. You might ask the following question: what would happen if instead of band insulator, this is a typical example, is on a band insulator, I had considered a one-dimensional model of a superconductor. Well, in a superconductor, there are certain nasty terms which look like CK dagger, C minus K dagger, spin up, spin down, with certain delta plus emission conjugate. This is how the perturbation looks like. The particle number is not conserved. There are only pairs which appear and disappear, so the parity of fermions is conserved, but not the number of particles, parity of the number. Even goes to even, odd to odd, even and odd never mix up, but the particle number is not conserved. Nevertheless, if you calculate the ground state energy, if you diagonalize that Hamiltonian, this is possible. This is the famous Bardeen-Cooper-Schrieffer theory of superconductivity, what I'm talking about. If you calculate that, you will again arrive at this result. If you go to the Pilot's limit, to the model of the Pilot's transition, when you consider a coupled electron phonon system, you'll find again this one. And finally, and most importantly, if you simply go to the quantum field theory describing as a relativistic massive Dirac fermion in 1 + 1 dimension, you will again find this result. Instead of delta, you will get the Dirac mass. Instead of T naught, you will get some cutoff. But essentially, it will be just the same. Which proves that physics is unique. It's the same subject realized in many different ways. In condensed matter, on high energy physics, this is the consequence of two things, of the massiveness of the excitation. The electron must be a massive. Second point is the theory must be effectively Lorentz invariant at low temperatures. And thirdly, the dimensionality of space-time must be 2, one space, one time. If these three conditions are satisfied, this is universal. So it's a very strong result, and people who were at the heart of the development of all these fields, both in condensed matter and high energy in the 60s, the 70s, perfectly knew all this, and it was the source of mutual inspiration. They used to see each other and collaborate and do many interesting things. Any questions here? Because at this point I close this chapter and we pass to another one. Is anything unclear? Again, it's up to you to choose the way to derive the properties of an insulator. You can follow the logarithm transformation UV, but with U squared plus V squared equal to 1 as it given in my lectures, if you prefer. Or you can follow this way. I just give you in parallel. It's a matter of taste. All right, so we are coming to the very, very last topic of our discussion. In previous years, I never touched it complete at all. Instead, I would jump to the pulse transition to the coupled electron foreign system, which is also interesting. It's very interesting because of the issue of fractional charge. You'll find excitations of topological origin which carry not the charge E, but E divided by 2. It's a it's a very strange thing which may happen, but it did happen. It has been observed and confirmed. But now I decided that after all the courses called many-body effects, and for many-body effects I would like to show you a very simple, not to say an elementary level, a very simple problem which shows you how a collection of interacting particles can exhibit properties which cannot be anticipated at the one particle level. Because the problem we are considering so far were one particle problems. We took the one-dimensional metal, one-dimensional for simplicity. It's a free Fermi gas, all the latest. All the states are well known. It's a one-particle states. How to fill them? We know when we perturb the system, it's again perturbation at the level of one-particle potential. Delta is a sign alternating potential. It's not a usual potential, but still a one-particle potential. So it's a high time to ask what to do with the interaction between the particles. Now I know that with many-body phenomenology part, which you have with the Professor Kisselberg, you have touched upon the Fermi liquid properties and Coulomb interaction affairs and the ways to describe it, so you know these effects are quite important. I will do the same, but I will do the same on the lattice, the way as close to what we've been doing as possible. Just not to go far away from our main line, basic line, right? So I once mentioned that the notion of localized spins applies to those systems who consist of atoms whose atomic shells are inner atomic shells. D or F shells are partially filled. And depending on the number of those D or F electrons, these localized spins, according to the Hund's rule, may be this or that. They may vary from 1/2 to 1 to 3/2 to 7/2. You may have even large values of the spins, and then, because of the very tight location of the wave functions of these D or F electrons, the overlap of these wave functions on nearest neighbors' sides is extremely small, and if you basically forget it, you can't fully forget it, completely forget it, but in the end of the day, you are left with the spins, and you don't think much about the delocalization of those electrons which carry those spins. Well, it's clear that if I insist on saying that I do need to take into account the effects of delocalization of those deeply located electrons, whose energy is very, very small, whose wave functions are very, very tight, and whose overlap is also small. Nevertheless, I would like to take these effects into account because there are some metals, especially transition metals, transition metal compounds, whose properties are determined by narrow bands formed due to this small, weak overlap of the wave functions of the inner d electrons. Now, what happens when you have this kind of electrons with narrow bands? The electrons spend most of time on the orbitals, because when the band is formed, you remember, right? So we have an n-fold degenerate level. If tunneling is forbidden, when tunneling is allowed, what happens? This n-fold level unfolds into a band. In our case, it may be something like epsilon of k minus twice t cosine of k in 1D case, for instance. So you have this band along states. And this, the bandwidth W is of the order of 4 times t. Right? This is the bandwidth. Now, according to the uncertainty principle, I can take this W multiplied by t and say this is of the order of h, Planck's constant. What is t? What is the physical meaning of t? And the physical meaning of t is as follows. If W goes to 0, when W goes to 0, that means you completely killed any tunneling. You go to the atomic limit. You forbid the electrons to hop from side to side. You go back to this. From this, you go back to this. Right? But this is the limit when all electrons are localized. So they will spend infinite time at their own orbitals without hopping to nearby. So therefore, if I switch on a finite W's, finite, by the way, I have to apologize. This is T naught and this is T, this is time, this is time. I'm sorry. Bad notations, I'm sorry. But if T naught is non-zero, therefore, the quantity T divided by, defined as H divided by W, is roughly turns out to have finite time spent by an electron at its own lattice side, where it comes from. But then eventually it goes. It's all the localization time, right? So the electrons spend huge time, most of time, sitting on its own side, on its own orbital, only randomly from time to time, not very often. Once in a way upon a time, so something happens, it delocalizes, it transforms to a plane wave eventually. So this is the regime of very narrow bands and long times for the electrons of being observed as a well-defined electron on at atomic limit. This is why we call it atomic limit. Since the electrons spend so much time at its own orbital, you can consider an electron with the given spin projection and you ask yourself, what will happen if you put another electron onto the same orbital, but with the opposite spin, of course, because the Pauli principle does not allow you to. Because if you want to put with the same, you have to do with the same spin, you have to push it upwards and take another level. And then the Hund's rule, whatever, will play its role, but if you want to put them on the same level, right, so the spin must be opposite. But two electrons must repel each other. And since everything occurs within a single atom, it must be a huge, huge Coulomb repulsion between the two electrons with opposite spins. And that was actually the first thing that people in the 60s were concerned. They wrote this term, the electron number with the spin up at the given site I, the same here with the sign down. If you have nothing, and if one of them is 0, then you have nothing. This interaction is out. But if each of them is 1, you cannot have more than 1, right? Then this coupling is U, and U may be very well much greater than T naught, than the bandwidth. So you have a strongly correlated system in which interaction prevails over the kinetic energy effects. So the total Hamiltonian then requires the following form. You write down something like, okay, you write down something like this. A chemical potential term, which controls the number of electrons at the given lattice site, minus T sum over ij nearest neighbors. I can absolutely safely consider only hopping between nearest neighbors because of the very strong localization of the wave functions on the lattice sites. Almost nothing. This overlap is almost negligible, but still I have to keep it to have something. But of course I can forget about the next nearest neighbors and so forth. So here I have Ci sigma dagger, Cj sigma between nearest neighbors automatically, and not plus this. So all the terms are very simple and straightforward. The chemical potential, something like you know very well, delocalization, tight body model, and on-site interaction. So this is the new thing. This term makes the problem not one particle problem. It's a many-body problem. Not like anything we considered so far. This is a brand new thing. Right? Well, in spite of its simplicity, apparently it's very simple. Well, apparently the Heisenberg exchange interaction also looks, well, when I said we never considered one particle problem, I was not quite right. I'm sorry, the problem of ferromagnetism or antiferromagnetism is not a one particle problem. It's a problem of many interacting spins. Quite another thing is that when the vacuum, when the ground state is identified, then the weakly excited states can be being thought of in terms of elementary excitations forming an ideal Bose gas. And that way you have a one particle problem, but not in terms of the original degrees of freedom. Right? Here the original degrees of freedom are already not one particle ones. So to make some progress, first of all, what we need to do is to understand the basic symmetry properties of this Hamiltonian. There are lots of symmetries here. All of them are equally important and they play a very important role. Well, first of all, if I take a specific lattice site I can build up a state of fermions characterized by the value of this occupation number, which may take values 0 and 1 for a given speed, right? That's all we can do. Pauli principle doesn't allow us to do anything. So the state of the given atom is therefore characterized by this pair of parameters for each speed projection. And what I may have is the state which is 0, 0, which means that this is a completely empty level, not a single particle. There is 1 and 0 here. Here I have a state with a speed projection as that 1/2. Or I have, and the charge, well, and the particle number, total particle number is 1, or I have 0, 1, and here z is -1 with the same particle number, or I have 1, 1, and here the z is 0, moreover the total speed is 0, as well as total speed is 0 here as well, and the particle number is 2. In these two states, the particle number is 1. Yes, it's 1. I already wrote it. Yeah. So it's a 4-dimensional Fock space at each Nersesyan. And these are just 4 states which you can equally build, calling this state as 0. Okay, let it be, this is 0. This is Ci up dagger 0. This is this one. This is Ci down dagger 0. This is Ci up dagger, Ci down dagger 0. This is the way how we build up the basis of 4 basis states with these eigenvalues of the corresponding operators, occupation number operators. So it's a 4-dimensional Hilbert space. We'll find out that these two pairs, this and this, play a very important but quite different roles in what follows. The first will be responsible for the charge excitations, and the second with the spin excitations. In other words, the full Fock space decouples into 2 invariant subspaces, sometimes built up in such a way that there is no connection between the two. They are quite separated. But of course, in physical problems, the truly genuine Hilbert space is 4-dimensional, and you have to explore all of them. Now, if you look here, the most transparent symmetry which is present here is, of course, the translational symmetry. You make a translation by full number of lattice vector, arbitrary number of lattice vector in any direction, in any dimension, or you could think of it in terms of hypercubic lattice. The Hamiltonian transforms to each other. It's full translation in the Now there is another thing. Looking at the construction which is given here, I would like to remind you again that this is an operator, the occupation number operator built up in terms of the creation and relation. Now imagine that I'm considering now a global U1 transformation, which is Cj sigma goes to Cj sigma I alpha. And alpha is a phase which does not depend on J. It's the same transformation for all the operators, and you can immediately see that this alpha in all these expressions will be cancelled. It's cancelled already here, but it's also cancelled here, and of course there. So there is a full phase symmetry of this homotic invariance with respect to the phase transformation. Well, in this point you recall something from early years when you were first learning things in classical mechanics. Well, under what circumstances the particle numbers, or maybe statistical physics, or maybe field theory, I don't know. Under what circumstances the particle numbers of physical systems are concerned? What is related to the conservation of the particle number? That's precisely the answer to this question. It's a global U1 transformation. There should exist a corresponding Noether current, so if you go to the field theory, for instance, in the field theory, you deal with the similar transformation of the field operators, and in the end of the day, you'll end up with the equation like this, which translates to the famous equation known as the continuity equation, which couples the density of the current of the matter. This is what you find in field theory, or classical field theory, or whatever. And as a result of this equation, if you take the integral over the volume, and use called the total charge, or total particle density, and then take the time derivative, you'll express it in terms of minus the divergence J times the volume over the volume, and then you will transform it according to the Gauss theorem. This is the dV as the surface, which is the boundary of this volume, and it will be J times ds. This is the element of the surface, and this is the flux of particles through that surface. And this flux vanishes. The particle number simply is conserved. It's, and you come to the conclusion that the conservation of the particle number, or which is the same as the existence of the continuity equation, which describes all this, follows from the global gauge symmetry. It's a global gauge symmetry of the system. There are phases you can always find such transformations which do it. Now, perhaps at this point I will stop, because we are also left with other symmetries which will take longer time. How to reach the spinous into symmetry is very important, and especially important is the particle Hall symmetry. All right, that's fine for this. Now, what I wanted you to tell, on the 4th of March, or on the 3rd of March, we have the final exam, right? Do you have any idea when what I found on the net, when everything is advertised and fixed? The day is fixed. The auditorium is just this one, but the time, strangely enough, is indicated as 11 o'clock. 11 o'clock. Now you don't have. It's not Wednesday. It's Tuesday, by the way. I don't know what is your schedule on Tuesday, on the March 4th. I assume that in the morning you are free. Is it correct?
Yeah.
Please check it. It's important. It's important because it's important for you. Please.
Tuesday, Thursday.
Do you have anyone on top of me on
Can
Tuesday?
schedule the exam, final examination for this course.
On 3rd of March, it is written that from 9 a.m. until 12:30 we have final exam in this subject,
Yeah,
and that's it.
Tuesday.
Ah,
That's
from
it.
9.
Yes, it's written like this. It's like anybody from
Okay. So I didn't reach this page because I was reading something outdated, perhaps. Yeah, all right. From 9. Very nice. Very good. It's even better. So we start at 9 o'clock and up to what?
12:30.
12:30 or 3:30. 12:30. 3 will be fine. Completely enough. All right. Okay, so it's settled, and therefore we are left with the final lecture the day after tomorrow, and on Friday we'll have a tutorial, which perhaps will be important. All right?